Welcome to The Deep Dive. We're the show that takes a deep look at fascinating sources to pull out the key insights, really helping you get informed without all the noise. So today we're tackling a big one. How much is the crazy fast pace of AI innovation actually tied up with, global trade disputes? It might seem like politics and tech are totally separate worlds, right? But we're going to uncover how these distant policy decisions, they have really tangible impacts right now. On the tech that's changing, well, everything. Our focus for this deep dive is this really complex, high stakes standoff. It's the US versus China over advanced semiconductor chips and those, super vital rare earth minerals. This isn't just some minor trade spat. It's fundamental, a struggle for tech leadership, and it's causing ripples everywhere. Defense, AI labs, you name it. And guiding us today, we've got some fascinating excerpts from a source called AI Acceleration, the US-China chip and rare earth trade. It's not just dry analysis either. It's got some telling insights, even predictions from an AI, Grok 4, which is pretty interesting in itself. Gives us a unique way to look at this whole thing.
Absolutely. And our mission here really is to unpack all the layers of this dispute. We want to understand the consequences, especially the unintended ones, and look at the sheer economic pressure that's building up. We'll explore why some kind of resolution seems, well, almost inevitable. But beyond just trade figures, we really want to show you the huge impact this whole situation and how it might resolve has on the global AI revolution. This isn't just about trade policy, it's about the future trajectory of innovation itself. How fast can we push AI?
Okay, so let's set the scene. Where did this all start? Well, the US government made a pretty big move. They put a ban on selling their most advanced semiconductor chips to China. Now, on the surface, the goal was clear, right? Strategic. Slow down China's tech progress, particularly in those really critical areas like AI, supercomputing, advanced military stuff. The ideal is basically cut off their access to the absolute top-tier components needed for, next-gen AI. Keep the US ahead.
Yeah.
Seems straightforward.
Exactly. That was the stated intent. A very clear strategic goal. Limit China's progress, create a bottleneck. But here's where it gets really fascinating and honestly a bit counterintuitive based on our source. While the aim was specific, the actual effects were much broader and unexpected. It seems the ban didn't just slow China. It might have inadvertently slowed down the pace of overall AI innovation.
Yeah.
Globally.
Globally, wow.
Yeah, it just shows how incredibly interconnected the whole tech ecosystem is. You pull one string, even a targeted one, and it sends ripples, shockwaves, really, through the entire system, things you didn't foresee.
And China didn't sit back, did they? Their response was quick and it hit a nerve. Direct retaliation, banning the export of rare earth minerals back to the U.S. Not symbolic at all. This was aimed right at a known vulnerability, maximum leverage.
Maximum leverage is right. And we need to be clear about what rare earths are. They aren't that rare geologically, but they're absolutely essential. We're talking 17 metallic elements crucial for, well, almost everything modern. Your smartphone, full of them. Electric car motors, batteries, wind turbines, MRI machines, fiber optics, and critically, the high-tech stuff, semiconductors, defense systems. They all need specific rare earths. But China's real power here isn't just digging them up, though they do have reserves. It's the processing, turning that raw ore into the super pure, usable materials needed. That's complex. It's messy, energy intensive. And for decades, China basically cornered that market, invested heavily, dealt with the environmental side, while others, frankly, outsourced it.
So they built up this dominance.
Exactly. Now they control something like 90%, maybe more, of the global processing capacity. So when they banned exports to the U.S., it was like shutting off a main valve in the global tech supply chain, left the U.S. scrambling for alternatives that just weren't there short term.
And the source describes the immediate effects on the U.S. economy, the defense industry, as devastating. So not a small hiccup, a major shock.
A major shock, absolutely. And this brings us to what's maybe the biggest aha moment from the source for you listening. The primary impact of the U.S. chip ban, weirdly enough, wasn't just kneecapping China's AI efforts. It actually seems to have slowed down global AI innovation. Think about it.
How so?
By restricting those critical chips, it created a drag on the whole system. It affects everyone who relies on that cutting edge, including the U.S. itself. So rather than just hindering China, the main effect was making it harder for everyone to push AI forward as fast. And this, incredibly, created an opening, an unexpected situation that, according to our source, ultimately works out better for China in the long run.
Wow.
It's a classic case, really, of complex systems responding in ways nobody fully predicted. Policy designed to weaken a competitor, it inadvertently created conditions where they could actually get stronger in some key areas.
Okay, this is where the story gets, really interesting. You've got This U.S. policy, the chip ban, right, explicitly designed to slow China down technologically. But what happened next was almost the complete opposite. This restriction, it didn't just fail to hinder, it actually seems to have massively accelerated Chinese innovation, specifically in chip design and related AI tech. It really drives home that old saying, necessity is the mother of invention.
It really is. And the how behind this acceleration is pretty clear when you look at it. It was basically forced self-sufficiency. When the door slammed shut on getting those top-tier foreign chips, China didn't just, give up.
Yeah.
The government funneled enormous amounts of money into domestic R&D. Companies that used to rely on buying components, they had to pivot hard. Intense internal innovation became the only option.
So a huge internal push.
A massive push, leading to this surge in homegrown technological breakthroughs. Chinese engineers, Chinese companies, they were basically forced to develop their own alternatives. And it wasn't just about copying, it was about building their own fundamental capabilities right across the board, from research to manufacturing processes. We've seen this pattern before with sanctions maybe, but the speed and scale here are really something else.
And the really surprising part, maybe even a bit unnerving for some listeners, is that specific innovations coming out of China now are not just good enough. They're actually crucial for US AI developers too. You might think they'd just be playing catch up, but nope. They've actually contributed some fundamental pieces to the global AI puzzle, stuff that's now core to the most advanced models we see.
That's absolutely spot on. We're not talking minor tweaks here. These are foundational contributions really shaping how AI models are built and run everywhere. Let's get into some examples from the source because they're quite telling. Okay, first up, MOE, or mixture of experts. This is a really big deal for making massive AI models, especially large language models or LLMs, much more efficient. See, traditionally, an LLM uses its entire network, all its parameters, for every single calculation. Massively computationally expensive.
Right, takes huge amounts of power.
Exactly. MOE, which has seen significant advancements from Chinese firms, though pioneers like Google also worked on it, allows the model to be smarter. It only activates specific expert parts of its network depending on the task. Think of it like having a team of specialists. Ask a history question. Only the history expert activates. This slashes the compute needed for training and, crucially, for inference that's running the AI day to day. It means you can build much bigger, potentially smarter models without needing exponentially more power. Makes advanced AI way more practical.
Okay, that makes sense. More efficient. What else?
Next is MLA, or multi-layer attention. Now, attention mechanisms are basically the heart of modern AI, like transformers, the engines behind ChatGPT and similar models. They let the AI figure out which parts of the input data are most important. MLA pushes this further. It lets the model focus on different parts of the input at multiple levels of detail at the same time. This is vital for understanding complex relationships, like nuance in long texts or intricate images.
So seeing the forest and the trees simultaneously.
So kind of, yeah. It leads to more accurate, more capable AI. Chinese researchers have really pushed forward ways to optimize and scale up these MLA mechanisms, directly improving how well large AI models perform.
Interesting. And there were others.
Yes, definitely. Another key area is advanced packaging techniques for AI chips. This sounds super technical, and it is, but it's incredibly important. It's all about how you physically put the different bits of an AI chip together, the processing cores, the superfast memory, the connections between them into one package. Traditionally, it's one piece of silicon. Advanced packaging lets you stack multiple chiplets vertically or place them very close together side by side. Think 3D chip building.
Ah, okay. Squeezing more power into less space.
Exactly. Better performance, less power needed, much higher density. Chinese companies have made significant strides here, developing techniques that are vital for building the next, even more powerful generation of AI hardware, especially with managing heat and data speed. This really challenges the idea that the West dominates all aspects of chip making.
Right. And one more you mentioned.
Yes, memory-efficient inference pipelines. As AI models get bigger and bigger, just the amount of memory they need becomes a massive headache. Running these giant models, especially not a huge data center maybe on your phone or in a car, can be really difficult or slow. So Chinese innovators have developed clever ways, combining software and hardware tricks, to run these huge models using significantly less memory when they're actually doing their job, the inference part.
Making them usable in more places.
Precisely. This is critical for actually deploying AI widely, getting it out of the lab and into real-world products and services, from smart assistants to factory robots. So connecting this back to you, listening at home or, wherever, These aren't just academic papers, these advancements. They're why the AI tools you use feel faster, smarter, more accessible. They're fundamental building blocks of modern AI. And the fact that they were developed significantly advanced within China during this period of restriction shows incredible capacity for rapid indigenous innovation.
And the story doesn't stop at design, does it? The source makes a really striking prediction about manufacturing itself. It says leading Chinese companies, specifically Huawei and Biren, are expected to be fully manufacturing state-of-the-art chips, SOTA chips, by late 2028. That's really soon, just a few years out.
It's incredibly soon, and the implications are enormous. We're not just talking about designing the chips anymore, which, as we've seen, they're clearly capable of. This is about having the full stack capability, the advanced factories, the manufacturing prowess to produce these cutting-edge chips at scale using the most advanced processes available. For years, that capability has been concentrated, mostly TSMC in Taiwan, Samsung in South Korea. If Huawei and Biren achieve this SOTA manufacturing by 2028,
It changes the game completely.
completely. It means China essentially closes the loop. Full indigenous capability, from design right through to leading-edge fabrication. That fundamentally reshapes the global tech landscape. Supply chains, national security, technological leadership, everything shifts. It strongly suggests the ban, far from halting their progress, actually spurred them to achieve this independence much faster than most people thought possible. So stepping back, what does it all mean? The source's conclusion is pretty stark, quite clear. This whole chips and rare earths conflict, which started as a U.S. strategy to maintain an edge, it seems to have inadvertently made the U.S. relatively weaker in some ways and China stronger, particularly in fostering this domestic tech ecosystem. It's a surprising outcome, but the evidence laid out is compelling. The restriction didn't contain, it catalyzed. Okay, now let's pivot to that prediction from Grok 4 because it's very specific and quite impactful. It states, by November 2025, the United States will likely be compelled to sell China its most advanced semiconductor chips. November 2025. That's, what, less than a year from when this prediction was likely made. It points to some really intense escalating pressure.
That is incredibly specific and near term. So, okay, let's unpack that. What are the core pressures that Grok 4 sees building that would force such a major policy reversal, compel the U.S. to do this within months? It can't just be abstract economics. This must be hitting hard somewhere crucial.
Exactly. It's hitting the supply chain hard. The source identifies the main driver as the urgent need to avert escalating supply chain crises from rare earth restrictions. This isn't a future worry, it's happening now. We're talking about stockpiles of essential rare earth materials, materials the U.S. needs for its own manufacturing, just running dangerously low.
The ones they stockpiled before.
Precisely. And at the same time, global demand for everything. These materials go into AI, hardware, EVs, wind turbines, you name it, is just soaring. So dwindling of supply, rising demand, and the critical piece. The U.S. still has insufficient domestic processing capacity. They might mine some raw ore, sure, but turning that ore into the ultra-pure metals and oxides needed for high tech, that crucial step, that's the bottleneck China controls. Without that processing, the raw ore is almost useless for advanced applications. It's a strategic choke point, and we really need to hammer this point home. China controls over 90% of global rare earth processing. This wasn't an accident. It was decades of strategic investment. They built the infrastructure, often taking on the environmental challenges others avoided.
90%, that's overwhelming dominance and a critical step.
It is. Think about specific examples. Cerium oxide. Sounds obscure, right? But it's absolutely essential for polishing silicon wafers perfectly flat during chip manufacturing. It's called CMP, chemical mechanical planarization. No high-purity cerium oxide. Your multi-billion-dollar chip fab grinds to a halt, period. Or take gallium, crucial for high-frequency semiconductors, the kind you need for 5G base stations, advanced radar, sophisticated military electronics. Again, not just a minor ingredient. Foundational.
It really brings home just how deep this dependency goes. It's not just assembling gadgets. It's woven into the very fabric of the material science that enables our digital world. It's a vulnerability many probably don't even realize exists until, well, something breaks.
And that's exactly the vulnerability the source points to. This reliance exposes vulnerabilities that could halt fabrication lines if these rare earth restrictions from China continue or tighten. It's not if, it's when the stockpiles run dry. And look at the production numbers. The disparity is just stark. New U.S. facilities like MP Materials, they're ramping up, sure, but projected output for 2024, maybe 1,300 tons of neodymium praseodymium oxide, a key magnet material.
Okay, 1,300 tons in China.
China. They produce the equivalent of around 300,000 tons of rare earth magnets annually.
300,000 versus 1,300.
Yeah. It's over 230 times more. It shows just how impossible it is for the U.S. to replace that supply domestically overnight or even in a few years. The scale is just orders of magnitude different. There's no quick fix here, even with massive investments starting today. The lead time is huge,
Yeah.
and we've already seen the pain. The source mentions a specific instance. A 2-month restriction period in 2025 caused neodymium oxide prices to spike by 65%.
Wow, 65% in just 2 months.
Exactly. That kind of volatility, it kills manufacturing planning. It destroys margins. It ripples through costs for everything using those magnets. These are the immediate, painful pressures forcing industries to demand immediate trade-offs. It reaches a point where upholding the current restrictions becomes economically devastating, just unsustainable. The logistics, the economics, they're pushing hard for a policy change, regardless of the original strategic thinking. So let's game this out. What if the U.S. doesn't concede? What if they hold the line and refuse to sell those advanced chips? The source lays out some pretty staggering economic costs. Just in the semiconductor sector alone, the estimate is $50 billion annually in losses if those sales to China remain blocked. That's not just a dent. It's a massive blow to a cornerstone U.S. industry. And these aren't just numbers on paper. This comes from real stuff. Production lines slowing down, even stopping, because they can't get essential materials derived from rare earths. Orders going unfulfilled. Imagine these incredibly complex, expensive chip fabs designed to run 2004/7, suddenly idling because one tiny crucial component isn't available thanks to the rare earth squeeze. It causes shortages all the way down the supply chain.
50 billion just for semis, that's huge. But how does that kind of loss filter out? What's the broader impact beyond just the chip makers' bottom lines? Does it affect, say, national security?
Directly. The source estimates an additional $20 billion in defense disruptions. And this is an abstract risk. It's concrete impacts. Take the F-35, we mentioned it before. Each jet needs about 417 kilograms, that's over 900 pounds of rare earths, for its engines, sensors, stealth materials, everything.
900 pounds per plane.
Per plane, without a steady supply. F-35 assembly lines could face serious slowdowns, maybe even halts. That means delayed delivery of critical fighter jets to the U.S. military and allies. And think about advanced missile systems. They rely on elements like dysprosium, another rare earth, for things like high-temperature performance in motors and precision guidance systems. If that supply is checked off, the reliability, the effectiveness of key defense capabilities is put at risk. It really forces you to ask, what does this dependency mean for actual military readiness, short-term and long-term? It could mean delays in getting next-gen tech deployed, maybe even eroding that technological edge the U.S. counts on.
Okay, so semis and defense. What about other tech manufacturing?
That gets hit too. The estimate there is another $30 billion in added costs for broader tech manufacturing. Same reasons. Rare earth price volatility making budgeting impossible, actual supply stoppages for components needed in everything from consumer electronics to industrial equipment. This makes U.S. manufacturers less competitive globally. If your costs are suddenly higher and your supply chain is unreliable compared to someone in, say, Europe or elsewhere in Asia, you lose business. And here's the kicker, the really tough part. The source emphasizes that alternative sourcing remains unviable without a decade-long build-out.
A decade.
At least. Building new mines, new processing plants, refineries outside China, it's a monumental task. Huge investment, long timelines, complex environmental hurdles. You can't just flip a switch. The dependency is deep, and unwinding it takes serious long-term commitment. So, add it all up, the direct hits, the indirect cost. The source projects that continued restrictions would lead to a total U.S. GDP erosion of around $100 billion by mid-2026.
$100 billion off the GDP. That's a significant drag on the whole economy.
A very significant drag. And we can break that $100 billion down a bit to see where it hits. $15 billion of that could be lost output in electric vehicles. EVs.
Why EV specifically?
Magnets. Those high-performance rare earth magnets are essential for EV motors, also for things like regenerative braking systems. Shortages there mean fewer EVs produced, slower adoption. Another example, potentially $10 billion lost due to factory automation downtime. Modern factories depend on sensors, robotics, control systems, all using rare earths. If those systems break down or can't be built, production lines stop. That affects everything from cars to washing machines.
Okay, so we're talking major industries getting hit, GDP taking a knock, but bring it down to the individual level. What does this mean for the average person, listening to this right now? How does it affect their wallet?
Directly. It means higher prices. The source estimates these pressures could inflate consumer prices by 5 to 10% for electronics and cars.
5 to 10% higher. Ouch.
Yeah. When manufacturers pay more for parts, or when stuff just gets scarce because production is delayed, those costs get passed on. Your next phone, your next laptop, your next car, potentially significantly more expensive. That hits household budgets hard. And this leads us to the ultimate irony, the really paradoxical national security outcome here. Despite the whole policy starting with the goal of strengthening U.S. national security by limiting China's tech, the actual result, according to this analysis, it's ultimately weakening national security through diminished AI and military tech advancement.
So the exact opposite of the intention.
Pretty much. By triggering this rare earth squeeze and the resulting economic damage, the very measures meant to secure a U.S. advantage end up hindering U.S. tech progress. Especially in AI, especially in critical military systems that rely on these materials, becomes a kind of self-inflicted wound, ironically making the U.S. less competitive and potentially less secure, not more.
Right. So given all the economic pain, the supply chain chaos, these completely unintended consequences, even the paradoxical security outcome, it's maybe not a huge surprise that the conversation is shifting. Our source points out that Chinese officials, manufacturers, they're saying the greatest benefit for everyone involved really lies in just resuming free trade, getting back to normal, so to speak.
That's exactly right. And the source itself seems to echo this, framing it almost as a global consensus emerging. The conclusion presented is pretty clear-cut. The greatest benefit to the U.S. and China, as well as to the rest of the world, and especially to the AI industry, would be to resume the free trade of advanced chips and rare earth materials. Notice the scope there. Not just good for the U.S. and China, but for the rest of the world, and especially for AI. The current situation, this view suggests, is basically throttling innovation potential for everybody.
Okay, so let's look forward then. If this prediction holds, if trade fully resumes maybe sometime after November 2025, what does that unlock for AI globally? What kind of boost are we talking about?
We're talking about potentially a massive boost. It would powerfully boost our AI revolution, as the source puts it. You can see why, right? Think about removing that huge uncertainty, that massive constraint. Suddenly, you have stable, predictable supply chains for the absolute cutting-edge chips and the essential rare earths needed to build everything around them. It frees up researchers, developers, companies everywhere to focus their brainpower and their investment on actually advancing AI, on building the next generation of models and applications, instead of constantly worrying about sourcing critical components or dealing with wild price swings or navigating geopolitical minefields.
It takes a major headache off the table.
A massive headache. It allows for smoother global collaboration, it fosters more stable supply chains, which benefits everyone, and ultimately, it leads to a shared acceleration of innovation. When the best ideas, the best components, the essential materials can flow more freely across borders, the pace of progress in AI is just bound to pick up significantly. It likely means faster training of more powerful models, quicker development cycles for new AI tools, and maybe even a wider, more equitable spread of AI's benefits across different industries and different parts of the world. It suggests a future where, yes, there's competition, but it exists alongside a level of cooperation and open exchange that fuels faster progress for all. In zooming out, I think this whole deep dive really underscored a fundamental point about technological progress today. It's deeply interconnected. No single country, doesn't matter how powerful, can really lead or innovate entirely on its own anymore, especially not in something as complex, as resource-hungry, and as globally collaborative as artificial intelligence. This whole U.S.-China chip and rare earth saga, it's a powerful case study showing that a future where AI truly thrives, benefiting everyone, is much more likely when trade flows more freely. When you have that open exchange of both the finished tech and the fundamental materials needed to create it, it's a reminder maybe that even between rivals, sometimes open doors lead to faster progress than closed ones. Hashtag tag outro.
And that really brings us to the end of this deep dive. What a journey, huh? We started with that U.S. chip ban, saw how it paradoxically spurred Chinese innovation, then dug into the intense economic and security pressures from the rare earth squeeze that now make a policy reversal seem likely. And finally, we touched on why resuming that free trade could be such a powerful catalyst, especially for the future of AI globally. It's an incredibly complex picture, isn't it? Where actions can have reactions you just didn't see coming.
It absolutely is complex. And I think this deep dive really highlights something crucial, how these global dependencies and trade policies, even policies designed with, national security front and center, can have these intricate, often unexpected, sometimes completely paradoxical effects on technology. It's a real lesson, perhaps, in how the costs of trying to restrict flows of critical goods and knowledge can sometimes spiral, potentially outweighing the intended benefits, especially in a field moving as fast as AI.
So, as we leave you with that, maybe think about what stands out most to you about this deep entanglement of national interests and global tech progress. And what could these lessons mean for innovation beyond just chips and rare earths as we all navigate this increasingly AI driven future? Definitely something to chew on. Thanks for joining us on the deep dive.